Hi, this is Mr. Barrett, and what I want to go over with you is how to actually solve questions number from Chapter 5, 73 and 76. So I'll be solving both of those problems for you right now. So here's problem number 73 from our textbook. And problem 73 gives you some very useful information. It gives you a chemical equation that shows the combustion of acetone, 1 mole of acetone in particular. And the formula for acetone is C3H6O. It's liquid in this combustion, and then it's reacting, of course, with oxygen because all combustions are with oxygen. And then the products are 3CO2 gas and 3H2O liquid. And it tells you what the delta H is for the reaction, and delta H is negative 1790 kilojoules. Okay, so now what we're going to do is we are going to try and answer the question to calculate that enthalpy of formation for acetone. Now, let's just remember what the difference is between this reaction and what enthalpy of formation is. So the enthalpy of formation for acetone is going to be some number in kilojoules per mole. Let's just keep that in mind, okay? Now, let's look at this equation and break it apart based on the type of reactions that are needed to show what's being formed and what's being broken apart. So again, we have acetone. Let me write out acetone, C3H6O. And it's decomposing. It's breaking apart in this chemical change. So it's breaking apart into carbon, hydrogen, and oxygen. Again, I'm putting 2's here because of Hofbrinkel. Remember, they're diatomic. And then let's take a look at what's forming in terms of the carbon dioxide and the water. So for 3 moles of carbon dioxide to form, you need carbon plus oxygen, and it's 3, so I have to make sure this is balanced. So I need a 3 here and a 3 there. And I'm actually going to look this up in the back of our textbook, where in Appendix C shows the enthalpies of formation. And the enthalpy of formation for carbon dioxide is negative 393.5 kilojoules per mole. And there's 3 moles we're producing, so I have to make sure that I multiply this by 3. Now in this question, what we're trying to do is we're trying to figure out what it is for acetone. So I actually don't know how many kilojoules per mole it is. That's why I'm not writing it down. Let's continue on for the rest of the reaction. I have water, so I'm producing 3 moles of H2O, and that of course requires hydrogen and oxygen. And then I have to show it balanced, so 3 halves O2 and 3 H2. I look up its enthalpy of formation in the back, the heat of formation, negative 285.83 kilojoules per mole. And I have 3 moles of it. Okay, now this is where we just get to some algebra. So we know that this is breaking apart, so we know that at the very least its delta H of formation is going to be positive. We know that much. Well, we know that this, whatever the delta H is for this acetone, plus this is going to equal what we were given as information in the beginning of the beginning of the question, which is that the delta H for this whole reaction, the combustion of acetone, is equal to negative 1790 kilojoules. And since it's 1 mole that's reacting, we know that that's actually in kilojoules per mole, since it was 1 mole of acetone that reacted. Okay, so let's keep this in our mind. We know it's this reaction plus this reaction plus this reaction will give us this reaction. I can set that up as an algebraic equation. Watch how I do it. Negative 1790 kilojoules per mole is going to be equal to whatever this is, and I don't know what it is, so I'm just going to leave it as an unknown variable x, plus this, which is 3 times negative 393.5 kilojoules per mole. And don't forget, I was able to make this per mole, even though in the given information it was just kilojoules, because it was 1 mole of acetone reacting. If it was 2 moles, then I'd have to change that. So I'm going to add it to this, which is 3 times negative 285.83 kilojoules per mole, Okay, so I'm going to have to solve for x. So I'm going to take this number and subtract it from these two numbers added together. When I do that, I find that x is equal to 247.99 kilojoules per mole. All right, that's nice, but I just figured it out for what this is. That's acetone decomposing, breaking apart. I want to know what it is for it forming. So I want to know the opposite of what this delta H is that we found. So the delta H for the formation is going to be the opposite sign of whatever it was we just solved for. So delta H for the reaction, or for the formation of acetone, is actually going to be negative 247.99, which I'm going to round off to negative 248 kilojoules per mole. So there's a couple of key things to keep in mind when you're solving this problem. First off, you have to use the heat of formation strategy that we've shown before. Break everything apart. Remember, oxygen doesn't break apart because its heat of formation is nothing. We were showing acetone breaking apart, and that it added to all the other things would give us the value that we're looking for. But since we're looking for the formation of acetone, we have to change the sign for what we solve for. Now, we're going to do another problem. This time we're going to be doing 5.76a. All right. So for 5.76a, it's a couple critical pieces of information that we need. So in 76a, the question gives us, it's basically a Hess's law question. It gives us a bunch of different reactions and their standard enthalpies. So what we're looking for is the standard enthalpy of formation for B2H6. But we do know the enthalpies for the following three reactions, which I'm going to write out right now. Now, I'm just copying this down straight from the textbook. So there's no work that I'm doing yet. I'm just copying, making sure I don't make any mistakes copying. Now, the first one, the delta H, is given to us, standard enthalpy, and it's negative 2509.1 kilojoules, and I'll write out all the other ones for each of the other reactions. Okay, as you can see, it's a lot of work just to get this down on your paper. Now, what we're looking for is the enthalpy of formation of this. But this reaction right here shows it breaking apart because B2H6 is on the reactant side. So I want to somehow add these three equations such that B2H6 is being formed, and that's the only thing that's being formed. So if I want to show this being formed, that means I'm going to have to take this entire equation and I'm going to have to flip it around. So let me flip it. B2O3 plus 3H2O produces B2H6 plus 3O2. All right, if you're thinking in your head, hey, you flipped it. You got to flip the sign for delta H as well. You are correct, so I'm going to flip that sign. So it's now positive 2147.5 kilojoules. So now I can just ignore what I've written up there previously for that reaction. Now I have it written like this. So now I have to add these three equations together, and I have to add them in such a way that all I'm left with is producing B2H6. All right, so that means I probably want to get rid of this oxygen here. So let's look. I've got three O2s here, and then I look on the left side. I'm adding these guys up. I see 3O2 and O2 there. I also have water. I also have boron, and I have hydrogen. Well, we can probably figure out that it's going to be boron plus hydrogen producing B2H6. I also know that I don't want to show B2OF being formed, so I want to get rid of this. But to get rid of it, I have to have the same before as I have after. Actually, this is before and this is after the reaction. So I need this to be 2 and this to be 2. and then I can cancel them out on both sides of my reaction. So to make this 2, I'm going to multiply it by 2, and what I do to 1, I have to do the rest. So this 3 becomes 6, this becomes 2, and this becomes 6 as well. When I multiply by 2, everything, I have to multiply delta H by 2. So that's going to be multiplied by 2. So now, if you look at it, when I add all of these, I have 2B2O3 on the left side, and on the right side of all of these, I have 2B2O3. So these can cancel out. I'll cross them out just like this. All right, now I look at the waters. See how this water has 6 and this one only has 2? And this is the only other water in all 3 of these equations. So I need this to be 6. So if you're thinking, well, why not multiply that by 3? You're right. Multiply that by 3, it's now 6. That means I have to multiply everything else by 3. And that means, of course, since I multiplied this entire equation by 3, I have to multiply delta H by 3. So now I have 6H2O on the left and 6H2O on the right. Now they can cancel out. All right, now let's look at the oxygens. I have 6 O2s over here, and then I have 3 plus 3, which is 6 O2s on the left. Sure enough, they can cancel out. So what am I actually left with? I'm left with 4B plus 6H2 produces 2B2H6. All right, so now this is the heat of formation, not exactly for B2H6, but it's 2B2H6. I'm going to add all of these together. So I'm going to add, let me take out a different color here since it's starting to get a little messy. I'm going to add this to this to this. Don't forget to multiply it by which you multiplied those equations by. So I get that out. In my calculator, I end up getting, after I add all of those together, it's negative 2509.1 plus the 3 times negative 571.7 plus 2 times 2147.5. I'm going to double check my work after I do this. So I find that delta H for this equation right here is 70.8 kilojoules. All right, fantastic. But I want to figure it out for just forming B2H6, not 2B2H6. Notice how each of these are divisible by 2. Well, I can divide each of them by 2. Remember what you do to one, you have to do to the rest. So I end up with 2B plus 3H2 produces B2H6. Well, I divided all of them by 2, right? That means, of course, I have to divide delta H by 2. So delta H for this reaction, for the formation of B2H6, 1 mole of B2H6, would be 35.4 kilojoules. All right. Now, one of the things that we want to pay attention to, of course, is our sign. Make sure that we added all of these. I would double check your math. And sure enough, this is the correct answer. If you guys have any other questions, please shoot me an email or see me during tutoring after school.